Welcome back all of you. So, we are dealing with stress path in these lectures. So, in the last lecture we have discussed about some common cases, and to some extent now you are conversant with the plotting of stress path. Now, let us be a bit focused on the use of stress path. First, let us see the laboratory stress paths, mostly for triaxial testing. So, today's lecture will be about stress path for triaxial testing and very specifically for drained triaxial test. So, today's lecture is exclusively for drained triaxial test. So, let us start with the statement that all of these most of us know, but for completeness we need to understand this. The intermediate principal stress in triaxial test is either equal to sigma 1 or sigma 3. The effect of sigma 2 is not taken into account explicitly. A wide range of stress paths are possible by independently varying sigma A and sigma R. This we know that in the triaxial testing we have better flexibility in modulating the stress paths, or for very specifically when we have a stress path triaxial system, it is very much possible to vary the stresses to suit the requirements of whatever is the scenario existing in the field. Now, stress path gives a better representation of undrained test specifically when we have U measurement as compared to Mohr circle representation. Otherwise, also if you want to understand clearly how the failure is taking place, at what instant the failure would happen and why it is happening at that particular instant, these informations are not available when we plot the stresses in terms of Mohr circle. So, stress path is much more handy in understanding this, and to some extent you have already appreciated this point in the last few lectures. And it is very specifically for undrained test that also we need to keep in mind, because it clearly shows how the undrained stress path it routes to its failure. Representation of failure progression by stress points are convenient, specifically when we do it on Q P dash and T S dash plot. Hence, stress path method can be a convenient replacement of a Mohr circle for triaxial test representation. But having said that, we need to keep in mind that if our primary objective is to obtain shear strength parameters, even plotting Mohr circle or TSS dash plot also would do. If we want to understand further the not failure mechanism, the progression of failure, then stress path would be much more handy. Another aspect before we start seriously into the stress path plotting, we need to keep in mind that the stress path has to be indicated by arrows, because we have to specify the direction in which the progression is happening. So, arrows are a must for stress path. So, let us start with different cases of drained stress path for triaxial tests. So, the first case is drained compression with constant radial stress, and it is designated as D1. So, it is the conditions are given already. Its constant radial stress means sigma R is not changing. So, compression is brought out by sigma A. Now, this is a very typical common triaxial compression test. In drain test, total and effective stresses are same, and hence TSP is total stress path is same as effective stress path. U is assumed to be 0. Now, there can be possibility of initial pore water pressure within the sample because of back pressure. Even if it is there, then it acts like a static pore water pressure as we have seen in the previous lectures. Then the total stress path and effective stress path will not be same, and this we will be discussing towards the last part of today's lecture. Initial stress conditions are considered to be isotropic. So, that is a starting point which is designated as M. So, we keep everything same as that of the triaxial testing condition, simple triaxial testing. Now, if we want to create anisotropic consolidation, that is also possible, but we are going ahead with simple initial isotropic stress condition. So, now we are plotting in terms of all the three stress paths, but later you will see that we will adopt any one of these stress paths as and when the depending upon the convenience. So, it can be TSS dash or QP P dash plots. So, now let us first start with sigma A dash, sigma R dash plot. It is given the isotropic is the starting point, and we should not have any difficulty in identifying this because it will be on the 45-degree line. So, this is the starting point M, and similarly for TSS dash it is M on the isotropic line and QPP dash M. So, let us start now how the stress path will move. It is constant radial stress. So, compression is caused by increase in sigma A dash. So, it is clear now these things have to be kept in mind. So, it is increase in sigma A dash, and hence delta sigma A dash is equal to plus delta sigma A dash. This aspect again we have discussed in the previous lecture. So, depending upon whether it is increase or decrease, whether it is compressing or loading or unloading, accordingly the sign of the increase would change or increase or decrease would change. So, here it is brought about by increase in sigma A dash. So, delta sigma A dash, and constant radial stresses means it is not changing, delta sigma R dash is equal to 0. Now, for sigma A dash sigma R dash plot there is nothing great because it is a direct replication of what the stress path would be, and it is very easy to plot. So, this will be the designated stress path D1 for in this particular plot. Now, how it will look like in TSS dash plot. So, you just need to substitute this, and that is where we have to be careful about. While substituting, do not forget to put the sign. So, here it is delta sigma A dash minus 0 by 2, that is plus delta sigma A dash by 2, here plus again delta sigma A dash by 2. So, it will be the slope will be delta T by delta S dash equal to 1. So, D1 is 1:1. Now, this again you have to keep in mind, like in TSS dash plot, if it is triaxial compression, the stress path, and for specifically for drained stress path, it will be at an inclination of 1:1 or 45 degrees. That aspect we need to keep in mind. Now, what will happen in QPP dash plot? Delta P dash is equal to plus delta sigma A dash by 3, Q is delta sigma A dash. So, delta Q by delta P dash is equal to 3. So, this is the next understanding in QPP dash plot. If it is drained triaxial compression, then the slope will be 3. So, this is D1 and this represented by 3. So, all the 3 has been done. So, this is the first case. Now, the second case is drained compression with constant axial stress designated by D2. Now, axial stress, there is a triaxial sample, there is an axial stress, there is a radial stress. How do we account for, or how do we bring about compression in this sample? It is told that sigma A dash remains constant. Now, what is the possibility of compression? A release sigma R dash. So, when you release it, there is a tendency to undergo compression under constant sigma A dash. So, compression caused by release of sigma R dash. Now, when there is a release, and here it is constant axial stress, so it is 0, and just because it is release, it will be minus of delta sigma R dash. So, in this plot, this is the starting point, A dash remains constant and sigma R dash is minus delta sigma R dash. So, it has to be in this manner. Okay. So, this is constant sigma A dash and this is decreasing, and finally it reaches the failure line, and that is given as D2. What about TSS dash plot? Delta T is equal to, remember, delta sigma A dash is 0 minus of minus, so that will become plus. So, plus delta sigma R dash by 2, here it will be 0 minus delta sigma R dash by 2, and hence the slope will be delta T upon delta S dash equal to minus 1. So, this will be minus 1 slope, and remember here again your delta T is positive, delta S is negative. So, you should be able to understand in which direction it will move. Minus 1 can be in this direction as well, but why it is specifically in this direction? Because S is going towards negative, T is going towards positive, as you can see here. So, that is why it is negative slope in this upward direction, and it meets the compression failure line. And what about QPP dash plot? So, delta P dash is equal to minus 2 delta sigma R dash by 3, and Q is equal to delta sigma R dash, because minus of minus, that will be plus delta sigma R dash, delta Q by delta P dash is equal to minus 3 by 2. So, it will be in this direction at a slope of 3 upon 2. So, this is the second case. Now, the third case is drained extension with constant radial stress. Now, if it has to create a sort of extension based on the compressive stresses, so how it will happen? It is told that radial stress is constant. Now, if extension has to happen, then we need to release the axial stress. So, that is why it is like kind of a squeezing effect. You are squeezing something, so it extends. So, that is the same philosophy that is adopted. So, here it is constant. So, the only possible way of extending is release sigma A dash. So, extension caused by release of sigma A dash. That is because of that it will be minus delta sigma A dash, delta sigma R dash equal to 0. So, A is moving in the negative direction. So, A is changing in the negative direction. So, that will be D3 and that will be downwards. Now, how it will be in TSS dash plot? So, delta T is equal to minus delta sigma A dash by 2, delta S dash is equal to minus delta A dash by 2. So, both delta T and delta S is changing towards negative direction, but the slope is 1. Both are moving towards, but then slope is 1. So, this slope, what is the sign of this slope and what is the sign of individual stress parameter also need to be considered. So, here it will be in D3 direction. So, this is positive 1 slope, but both are moving towards negative. So, this is negative S direction and negative T direction, and the same will be there for QPP dash plot. We have delta Q upon delta P dash equal to 3, okay, but in the downward direction. Now, the fourth case is drained extension with constant axial stress. Now, axial stress is remaining constant. Now, how do we bring about extension? If you want to bring about extension, you need to squeeze it. So, sigma A dash constant, so sigma R is increasing. So, extension caused by increase in sigma R dash. So, delta sigma A dash equal to 0, delta sigma R dash equal to plus delta sigma R dash. So, this is in the positive direction, that is represented by D4. What about TSS dash? Delta T is equal to minus delta sigma R dash by 2. Now, you can see that T should move towards negative direction. S is equal to delta sigma R dash by 2, and hence delta T upon delta S dash equal to minus 1. So, you will have from here it moves towards, you can see that S is in the positive direction, whereas T is in the negative direction. Okay, so, that is all about TSS dash. What about QPP P dash. So, P dash is equal to 2 delta sigma r dash by 3, that is plus delta q is equal to minus delta sigma r dash, hence q upon P dash is equal to minus 3 by 2. So, the slope is minus 3 by 2, it will move in the downward direction, that is for D4. So, these are the important possible 4 cases, one kept constant at a time. So, both compression and extension. So, this is a summary of drained stress path for triaxial test. Now, another important aspect which we need to understand is that depending upon the stress path, you can see that the failure when it is going to happen, that is also dictated by the manner in which the stress path changes. Let us say for the case of D1, you can see that so much of allowance is possible. So, the strength available is this. So, when it reaches here, it fails. Whereas, for D3, you can see that the failure occurs quite fast, even though the starting point is same, and that is true for all other stress path representation. So, this stress path representation also gives such insight as to same initial point, but depending upon the manner in which the stress changes, the failure condition also changes. To some extent, we have seen this when we discussed about shear strength tests. So, depending upon the manner in which the loading changes, it influences the failure conditions as well. So, now just summarizing this, these are the 4 different stress path directions. If I draw a line here, then because this is the starting point, above portion, this particular portion, it represents compression, because K it is dictated by what K you are talking about. Here it is sigma A dash is more than sigma R dash. So, it is compression. This region is basically for extension. From here towards this direction we talk about unloading, and towards this direction it is loading. So, all the cases have been summarized in this particular plot, and this x and y can be any of these stress parameters, either TSS dash or QP P dash. So, failure strengths in drain tests are governed by stress paths. For an identical initial isotropic stress state, we have Tf D1 equal to Tf D4. Now, we are talking in terms of T here. You can see that Tf D1 means the strength which is given by the failure stress path D1. So, this is what is meant by Tf D1. So, if I draw here Tf D1, that means it is the strength of the soil corresponding to the stress path D1. Now, D1, this stress path strength is same as Tf D4, but it is more like a mirror image. Similarly, Tf D2 is equal to Tf D3. Now, let us see the influence of initial state and cohesion on drained stress path for triaxial test. Now, here till now we have been considering C dash equal to 0. Now, let us see that what will happen if cohesion is there. Is there a significant difference from what we have learned, or how it changes? And the other aspect is the initial state. Initial state means isotropic consolidation, or whether it is a normally consolidated soil or any other K value which we tend to use. So, let the initial stress state correspond to K naught NC. Now, first case, let us consider K naught NC condition with K naught NC is less than 1. That means sigma A dash is greater than sigma R dash, a typical triaxial test that we normally do in the lab. So, we are talking now in terms of TSS dash, as I indicated before. We will not do for all the 3 now. As and where the case comes, we will generally use any one, and typically we will be dealing with TSS dash Q P P dash plot. So, now let us try to understand what will be the influence on stress path because of the initial state and cohesion. Now, initial stress state is given by S naught dash and T naught. So, the initial point corresponds to K naught and C state. So, if you draw a line here K naught and C, this initial stress state falls on that, and it is clear that it is K value is less than 1. So, we have already seen in the previous lecture, like if it is K value less than 1, which corresponds to sigma A dash greater than sigma R dash, it will be in the upper part or in this particular region. So, this is our starting point P. Now, to add value to this stress path plot, let us first draw the failure line. Now, you can see that it is no longer through the origin. There is an intercept here, and in TSS dash plot, what is the intercept? Definitely it is not C dash, it is A dash, and the relationship between A dash and C dash is already known to us. So, this is the inclination alpha dash or tan alpha dash, which is equal to sin phi dash, which we have already seen. So, this is alpha dash, and this is the point Q. So, this is A dash, which is the intercept in TSS dash plot. Now, if this is A dash, we can write this to be A dash cot alpha dash. Now, for drained stress path in compression, you can see that D1, which we have already seen before, let this point be S. Now, what has happened? Initially, this stress path started off from here. Because it is normally consolidated, so the point has shifted upwards, but at the same time the failure line also got shifted upwards, which means that strength because of C dash has been incorporated. This is the other stress path. So, we will be generally dealing with D1 and D2, both refers to a case of compression. Now, this particular point P is at S naught dash, the initial point, and this is T naught. We have also seen that if you know this particular point P, one can also find out what are the stresses it is subjected to. So, this is sigma A dash, this is sigma R dash. What we have to do? Draw a horizontal line, draw 45 degrees to both sides wherever it is intercepting the S line. So, that will give us sigma A dash and sigma R dash. This is already discussed. In that case, this will be T naught and this will be T naught. Now, what we are trying to do is we are trying to understand or determine what will be the expression for the strength represented by D1 and D2. Now, what is the strength? It is TF, that is a failure point in T. So, let us assume this point to be S and T. So, you are dropping a vertical from this particular point. So, let it be ST. Now, we know that this angle is 45, this angle is 45. So, this angle is 45 degrees, and this is alpha, and hence this is also alpha dash. Now, this is TFD1, that is the strength corresponding to the stress path D1 is given by TFD1. Since this is 45 degrees, take this triangle, this particular triangle, this is 45 degrees. So, here it is TFD1. So, definitely this has to be TFD1. Now, referring to this figure, QT is equal to, this is TFD1 divided by QT is equal to tan alpha dash. So, QT will be equal to TFD1 divided by tan alpha dash, that is QT equal to TFD1 cot alpha dash. So, what we are trying to do? We are trying to get an expression for TFD1. Okay. Now, what is RT? RT is equal to TF D1, that is already clearly marked on the figure. We can also write RT is equal to QT minus Q0 plus OR. So, that will give RT. So, we have the expression for RT TFD1, substituting that. We also have the expression for TFD1 QT, that is TFD1 quad alpha dash. QO is already marked here, A dash quad alpha dash, and OR, that is OR is equal to S0 dash minus T0. So, that will be OR. So, all these are known. Substitute it, we will get TFD1 equal to TFD1 quad alpha dash minus A dash quad alpha dash plus S0 dash minus T0. So, rearranging similar terms, then we will get TFD1 quad alpha dash minus 1. What we are taking is, we are bringing this to this and TFD1 on to this side. So, that will give TFD1 is equal to A dash quad alpha dash plus S0 dash minus T0 divided by quad alpha dash minus 1. So, this is about TFD1. So, we need to also find expression for TFD2. Let us see how. So, let us drop a vertical at U. This is TFD2, this is at an angle of 45 degrees. We can write UV is equal to TFD2 because this is 45 degrees. QU is equal to TFD2 quad alpha dash. This QU is equal to this one. So, that is very clear. We can also write QU is equal to Q0 plus OT plus TV minus UV, that will give you QU. So, all these are known to us. QU is TFD2 quad alpha dash, QO A dash quad alpha dash plus OT, this is S0 dash plus T0 minus UV, that is TFD2. Again rearranging, we will get TFD2 quad alpha dash plus 1 is equal to A dash quad alpha dash plus S0 dash plus T0. So, we will get the expression for TFD2 similar to TFD1, A dash quad alpha dash plus S0 dash plus T0 upon quad alpha dash plus 1. So, this is about the expression for both TFD1 and TFD2. Now, let us see what happens if k is greater than 1. So, earlier case was k less than 1, that is sigma A dash less than sigma R dash. So, where will the point start from? It has to be in the bottom portion. So, this same for the previous case. So, now you can see that the point P is in the bottom half. All other aspects remain same. Now, D1 it starts from here, then this is TFD1 same, and this is D2 and this is the strength TFD2. You can see that there are more elements now because it is starting from this particular point, it takes a while reaching the compression failure line. So, what is the effect? It has got shifted. Now, here this will be T0 T0 because why it is T0 T0 here? Because this is at an inclination of 1:1 or 45 degrees. Previous equations for TFD1 and TFD2 are valid for this case as well, but the only difference is at the starting point is below. So, the value of T0 will be negative. Okay, now let us see that what will happen if there is some initial pore water pressure. We know that there is a drained test we are discussing about, and we do not expect any pore water pressure development during shearing. But what if it happens that there is some pore water pressure in the beginning, and that we have seen there are different possibilities why there should be pore water pressure. A very good example is the presence of back pressure because of saturation. We know that it is a static pore water pressure, but then still that acts as a pore water pressure, and hence the stress path will be different, even though we know that total stress path and effective stress path are same in drain triaxial testing. You should not confuse why there is a contradiction here. There is no contradiction. The pore water pressure referring to is only the initial pore water pressure. So, drain compression for a normally consolidated sample with 0 increase in pore water pressure. Here you can see that you are discussing about initial, not during shearing. So, that is why it is 0 increase in U, means U is pore water pressure, but there is an initial back pressure which exists in the sample during saturation. So, again TSS dash plot, KFC has been drawn, the initial isotropic consolidation M is stated here. So, there is a back pressure. So, now the initial point, total stress point and effective stress points are different because of this difference in back pressure. So, now here it is M, here it is M dash. So, here the effective stress path is in this direction. Now, what is the slope of effective stress path here? We have already understood that in a drained triaxial compression in TSS dash plot it is 1:1, so 45 degrees. So, this is 45 degrees or 1:1. Now, total stress path will be parallel to effective stress path. Now, there is something interesting which is coming out here. Why did I stop this total stress path here? You have the failure line, it should have extended. Now, this could be an immediate response for some of you. Please note that failure is always brought about by effective stress. So, the failure is dictated by effective stress path. So, this is the effective stress path, it fails at this point. So, total stress path beyond this point is not meaningful because the soil does not exist. So, that you have to keep in mind. This is 1:1, I have already told. In the same condition for QPP dash is the same thing, only the slope changes, all other details remains the same. There is a parallel shift in effective stress path with a difference of back pressure. Shearing under different isotropic cell pressure results in different parallel ESPs. Again, it is better that we understand this point right now, because what it means is that now this corresponds to one particular effective cell pressure. Now, when we shear at different cell pressure in triaxial drained condition, we will have parallel ESPs. This is what it is, TSS dash, and this is the failure line. You can see that this corresponds to the first cell pressure, this corresponds to the second cell pressure, and this corresponds to the third cell pressure. So, these are different cell pressures. We can see that how the failure is happening. So, it is just a parallel shift in effective stress path. Now, let us deal with drained compression of over consolidated soil with 0 increase in pore water pressure. Earlier it is normally consolidated, now it is over consolidated. Initial back pressure exists. Now, remember this failure line corresponds to critical state friction angle. All those things we have already discussed. Now, with problem with over consolidated sample is that it exhibits peak and then fails at critical state or ultimate state. So, that is what why we have to specifically discuss it for over consolidated soil. So, back pressure exists, all other condition remains same. Now, you may ask here, we have already learned that in over consolidated state pore water pressure will be negative. You are correct, but that corresponds to shearing stage. Here we are referring to initial state, we are not started shearing. Negative pore water pressure happens because of dilation, dilation happens during shearing. So, do not have to confuse that. So, here other things remaining same, Now here the effective stress path is crossing the failure line. So what is happening? How can this be possible? There is no state of the soil that is possible beyond the failure state. Now here we have to be very clear about our understanding. In fact, the same aspect is going to be very clear when we discuss about yielding. Now here what has happened is the soil would fail only after exhibiting peak in the case of over consolidated. That means the yielding has to happen first, then only it will result in failure. But unfortunately this line corresponds to the critical state line. So soil has not yielded. So first it will go to the yield point and then it will come back to failure. So here it has reached the peak because it is always greater than the critical state. So it reaches the peak and then it comes down. You can see this arrow coming down and then it will fail at this point of critical state. So it goes up and then come down, and that is just because when you understand this vis-a-vis the stress strain response of over consolidated soil, which we have already discussed, this aspect will become very clear. Okay, and your total stress path will be up to this particular point. Now if you want to find out what is the pore water pressure corresponding to peak, then the total stress path will go here. So this is the difference. In fact, total stress path does not come into picture when we talk about failure. So this again the difference is back pressure. Here it is QPP dash, so the slope is 3. So during shearing of OC, it would reach peak state first. The stress then falls to critical state by strain softening. Okay. So that's all about triaxial testing, drained case specifically. We have not talked about undrained now. So what we have learned in this lecture, let us summarize. Triaxial drained SPs discussed, 4 well defined cases of compression, extension, loading and release combinations is discussed in 3 stress path plots. Drained compression loading, that means we are talking about increasing of the load, is at 1:1 slope in TSS dash and 3:1 slope in QPP dash. This aspect you need to keep in mind. That is for triaxial case, compression, and it is loading, that is increase in stresses. So it is 1, positive 1 and positive 3. Initial stress state, that is which is defined by the K value, and cohesion influences the stress path. We have clearly seen that. So here we have already derived drained strength TFD1 and TFD2. Presence of initial pore water pressure, how this would impact the stress path we have discussed. Even though in drained triaxial condition we do not expect ESP and TSP, but just because of the presence of initial back pressure, both gets shifted parallel to each other with a difference of UBP, that is back pressure. Shearing under different isotropic cell pressure results in different parallel ESPs. For drained shearing of over consolidated sample, the stress state reaches peak and then returns to critical state failure line. Now failure condition is totally defined by ESP and not by TSP. This is a very important point that we have to keep in mind. For drained shearing, ESP and TSP are same in the absence of initial pore water pressure. So some of these concepts are very relevant and you may be able to understand it very well, but then these points we need to keep in mind so that we understand it better. So that's all for today's lecture. We will see a few more cases, that is exclusively triaxial undrained tests and its stress path in the next lecture. Thank you.